Hey guys, in today's video we're going to be discussing reaction rates. So essentially the rate in which a reactant turns into a product. So we've talked about chemical reactions, we've talked about the reactants and the products, but we haven't discussed like how much time it takes to turn those reactants into products. So what a reaction rate is going to be the amount of time it takes to change that quantity of reactants into the quantity of products. So our general equation here that we use to define this is going to be a negative sign here. This symbol here, which is delta, means change in quantity over the change in time. So if you see here in our graph, we have all the purple cubes are our reactants, and so it's the amount of time that it's taking for those purple cubes to turn into green pyramids here in our diagram. And that's going to be our reaction rate. So again, this is our general reaction rate equation, but it's the same as the one on the other page. So what determines reaction rate is going to be the collision theory. And there's three main parts of the collision theory that we're going to go over. But generally what it says is that in order for a reaction to happen, the atoms of the reactants have to collide. So it is just as straightforward as that. In order for these two, A and B, to form a product, they have to collide together in order to form that product that they should be able to form. So what an activated complex is, after these two reactants collide, it is going to be this temporary arrangement of atoms in which all of the old bonds are breaking and the new bonds are forming. So not only though, and we'll go over this in a couple slides, not only do these atoms have to collide, but they need to collide in the correct orientation and with also the correct, or a sufficient amount of energy to cause the reaction to happen. So if we look here in this first diagram, so we, in this reaction here, we need the gray carbon atoms to collide with the red oxygen atoms. So in this first collision here, so not only do they need to collide, but they need to collide in the correct orientation. So we see the two oxygen atoms colliding. That's not what we want. We don't want the oxygens to form a bond. We want carbon and oxygen to form a bond. So what they end up doing is just rebounding apart. Again, same solution where we're combining these. Again, gray needs to collide with red, but in this one we have red with this green nitrogen here, and so it's not the correct orientation. They're going to rebound apart. The next one here shows us the correct orientation, the carbons colliding with the oxygen, which is what we needed. So they'll form this temporary arrangement here, this activated complex. This is where they need to break the bonds that they had originally. So this oxygen needs to break apart from the nitrogen and then form their new bonds here. So this oxygen then needs to form a bond with carbon. This one shows the correct orientation here, but we also need the correct amount of activation energy, or the amount of energy to get the reaction started. And since that does not happen here, then it actually rebounds again. So again, I've mentioned activation energy on the previous slide, but what that means is the amount of energy in which you need to get the reaction started. The amount of energy that's required for those reactants to have to get them to form their new bonds. If you have a high activation energy, then it means that it's going to take a lot of energy to put into that reaction in order to get the reaction started. Generally the reaction rate is very slow because there's not very many reactions, or excuse me, there's not that very many collisions that have that correct amount of energy. So for collision theory, we have these three main parts here. Not only do you need to have those reactants collide with one another, they need to also be in the correct orientation. And then the last piece is that they need to have sufficient energy to form that activated complex. So we're going to go over two different graphs here to show us two different types of reactions. Now, we've heard of endothermic and exothermic graphs before. I would not necessarily memorize these, but just look at the graph to see what it's telling you. If we just look at our axes first, we have energy on our y-axis, and then the reaction or time here on our x-axis. So as time's going on here, the reactants have more energy than the products. So what looks like has happened here, in order for that to happen, is that the reactants had to have released energy. And so if reactants release energy, or the energy moves out of the system, then that's called an exothermic reaction. So what we need to identify on these graphs is that the reactants here are going to be wherever we're starting on the graph. So the reactants are here, this line. Where you finish are the products. And then this hill that you need to climb is the activation energy. That's the energy you need to put into the reaction to get it started. At that peak there, that's going to be the activated complex. That's the temporary state in which old bonds are breaking and new bonds are forming. And then after we climb that hill, after we get the reaction started, the downhill process is the reaction coming to completion. And so energy here is being released since it's an exothermic reaction. So the difference between that activation energy and where the products end up is our energy being released. In this reaction here, it is, again, we're looking to see where the reactants are and where the products are. Our energy is still on the y-axis. Reaction progress or time is on the x-axis. So the reactants here have a lower energy than the products, which means that the products, like in order to get there, they had to have absorbed energy. So if energy is being placed into the reaction, then it's called an endothermic graph. So this is our endothermic reaction. Notice that there is a high activation energy here. Endothermic reactions require a great amount of activation energy, which means we're going to have to put a lot of energy, heat generally into that in order to get it started. The peak of the graph again is that activated complex. And then when here, wherever it falls to our product side, the difference between where it starts and where it's finished is the energy that's absorbed by that reaction. I'll go back. I was going to skip these, but in a later system we'll talk about thermochemistry, but thermochemistry is this study of the heat that accompanies chemical reactions. Now there are certain vocabulary words that go around or that go along with this. So system is going to be the part of the universe. So we have the universe, the system, and the surroundings. The system itself is where the reaction is happening. The surroundings are going to be outside of the system, so outside of wherever that reaction is happening is the surroundings. And then the universe is a vocabulary word that we say is the system plus the surroundings. So if you have, let's say for example, the system itself is the reaction. If it releases energy to the surroundings, then that's an exothermic reaction. If the reaction in which the system is taking place absorbs the energy from the surroundings, then that's going to be an endothermic reaction. We generally use enthalpy kind of as another word for heat. So enthalpy is generally defined as the system or the heat that's involved in that system. heat of reaction, enthalpy is usually represented by delta H of the reaction. And so heat of the reaction or enthalpy of the reaction we use here as delta H reaction to show that. Now if we use the enthalpy of the reaction in order to find that, we're going to take the heat, the final amount of heat, and then subtract the initial amount of heat from it. Another way we can do this is by taking our products minus the reactant. So the amount of heat or energy required from the products minus enthalpy of the reactant. So a thermochemical equation is basically a balanced chemical equation. It includes states of matter, the reactants, products, and energy changes, and we use that equation on the other side to show what kind of heat is gained or lost by that system. I'm going to skip that. I don't think that's in your notes. We'll just go ahead and go over these two, I guess. Enthalpy of vaporization means the heat that's required to vaporize a substance. And then enthalpy of fusion means the amount of heat that is required to melt a substance. So there's a couple of things that will affect our reaction rates. One is going to be concentrations. So when the concentration of the reactants is increased, it causes more molecules to collide, and therefore it increases our reaction rate. So if you want the reaction to occur faster, you could increase concentrations of reactants to increase that reaction rate. Surface area is another thing. So this is where we're breaking things into smaller pieces. If we take our reactants and make sure that they're broken up into smaller pieces, we increase the surface area. By doing that, we increase the number of collisions that occur between the atoms, and then this will also increase the reaction rate. Temperature is an important one because increasing temperature will generally always increase the reaction rate. And the reason why this is because it increases the kinetic energy of the particles. By increasing the kinetic energy of the particles, it means that they are moving faster. So these particles are moving faster, which means they're going to collide more frequently and with higher energy collisions. So with those two things happening, we increase the reaction rate, and generally that's how we achieve those really high activation energies. So what a catalyst is, that's also another way we can increase it, is a catalyst is going to be a substance that generally just increases the rate of the reaction, but it's not consumed in the reaction. So an example of this is enzymes. So enzymes that occur in your body help facilitate the reactions that need to happen. So like digestion, for example, those enzymes that are in your digestive system help speed the reaction up without being consumed. So they are not consumed in that reaction. They don't get taken up at all. They just come in, bind with reactants, and then eventually get released. Another thing is an inhibitor, and it kind of does the opposite. So it's actually something that slows down a reaction or prevents it from even happening. So what a catalyst does is it essentially lowers the activation energy. So if we look at this graph here, the reactant, like we would have had to have climbed up this really large hill here to get to this activated complex. But what the catalyst does is it lowers the activation energy. So if it's functioning at this blue line here, then more of these reactants can be converted into products. It happens much faster, and therefore it speeds up the reaction. A heterogeneous catalyst is going to exist in a different physical state than that of the reaction it catalyzed. And if it's a homogeneous catalyst, then it's going to be in the same exact state that it catalyzes. So again, here's your graph. This is pretty important. And hopefully, based on this, you get a better handle on, what affects reaction rates and